think I'm just gonna start now. Okay, I'll be teaching electromagnetism this session. This is my first time teaching, so I hope you can understand that it's gonna be a little bit shitty, but uh, I hope it's okay. Yeah. Um, I do not have a tablet, so I'm gonna be using a mouse for the meantime. So it's gonna be a little bit archaic. So please don't mind if my handwriting is very bad or anything. So yeah, without further ado, I guess I'll begin now. Okay. Wait, firstly, can I check if you can hear me? Because I can see the green circle. I assume you can hear me? Okay, you know what? I'm gonna assume that's a yes. Okay. Anyway, I'll just proceed. Oh, okay, yep. Okay, I'll proceed. So, I'll begin teaching a chapter. So, basically, magnetostatics, right, is, okay, previously we've been taught electrostatics, right, which basically deal with, charges, lah. So, charges, right, they exert their own, uh, electric field around themselves that look something like this. I'm not gonna draw too in detail because it's really difficult with a mouse, but you get the point. So in electrostatics, we usually deal with static charges, which exert their own like electric fields and stuff, and exert electric forces on other objects. In magnetostatics, however, we're mainly dealing with stuff like moving charges. So usually this can be like literally just a point charge that's moving at some velocity, or it can be like a current, because currents are actually filled with electrons that move in some direction lah. And here I indicate this as upwards, but the direction is downwards because conventional current points in the opposite direction to electrons moving lah. But yeah, so in magnetostatics, however, um, instead of electric fields, right, they still generate their own electric fields, but there is um there is its own like field that also comes from the movement of the charges themselves, and these are called magnetic fields. So, for example, a moving charge like this would generate a current that looks will generate a magnetic field that looks something like this and similar to that of this current here also. So these are what we would call like our magnetic fields are. So the similarity between electrostatics and magnetostatics, I guess a way to compare them both is that an in electrostatic situations, right, when we have charges, right, usually they only have divergence, while for magnetostatics they usually only have curl. Um, those terms probably only make sense to you if you know a bit of vector calculus, but basically it's just basically what I mean is that your electric fields, they only sort of spread lah, so they only have sources or sinks. As you can see, these fields emanate from this charge. However, for magnetostatics, right, usually there are no sources of sinks, so you can see all the behavior is usually rotational or something like that when you have like a charge, when you have a current coming out and it has its own magnetic field, stuff like that. So that's just a way of comparing that. But in essence, it in essence magnetostatics deals with magnetic fields, and I'm pretty sure you have learned some of these in your high school syllabus already, but we'll go a bit more in depth so in this session. So as I've introduced magnetic fields, they actually come from naming. It's actually only called the B field because of history, but I don't think we need to care too much. Just know that sometimes the magnetic field is also referred to as the B field, and it's also sometimes referred to as the magnetic flux density. So if you see that, just know that it means the magnetic field also. And yeah, we usually denote it by this vector quantity B lah. And we also denote the magnetic force as FB similarly, but we'll deal with those later. We'll just deal with calculating fields first. So the main methods of calculating magnetic fields are two laws, which are called the Biot-Savart law and the Ampere's law. And I guess there's also the Gauss's law for magnetism. But these three basically help us um, calculate magnetic fields in certain situations. So I guess the first thing to introduce is the Biot-Savart law. So this law allows us to determine the magnetic field in some region of space due to either some steady current or a moving charge, as I mentioned just now. Yeah. So, and it's given by this this integral, which looks a bit intimidating, but basically what this means is that, let's say you have some wire like this, and current is flowing this way, and you want to calculate the magnetic field at this point, and if this is the origin, this would be R, I guess. Yep, something like this. If you want to calculate the magnetic field here, right, what this integral means, right? Okay, actually no. First, what this small part means is basically, since there's some current I flowing through here, this ds is some small infinitesimal like vector on the wire. So that basically means something like, if we consider this small portion here, right, then this vector, this would be ds. Yeah. And then this r prime here, right, this r prime is not this position vector, but it is actually this position vector r prime lah. So that basically means, right, you take this vector, you cross this vector, and then you multiply that by the current, and then you divide that by this r prime distance all cubed lah. And once you integrate that over the entirety of the wire, and you multiply by this constant, you get the magnetic field lah. Yeah. And this constant, I think it's called the, I don't know how come I forgot the name, but I think it's called the magnetic permeability, the permeability of free space, I think. Yeah, permissivity of free space, something like that. Yeah, this is mu naught. But basically, this is just a scaling constant lah. But yeah, so the Biot-Savart law says that if you take this expression and you integrate it, and then you multiply with this constant, you get the magnetic field at this point. It sounds a little bit confusing, but I guess it's best to illustrate with an example also. Okay, I guess before the example, there's also this alternate form, which takes the current density instead. If you don't know what the current density means, it basically just kind of means the current per unit area. So for example, if you had some wire, something like this, and you had current flowing through it, some uniform current, let's say it's I, right? And this area here is A, then your this current density J is going to be your I over A lah. Yeah, I over A. And you also multiply by whatever this R hat is lah. But yeah, that's what the current density is, and it should be kind of easy to see how both of these are related to each other. And here you integrate it over the entire volume of space instead lah. And you should kind of see it because, okay, intuitively, right, you have this J times dV. You can separate your D into like dV into A. Sorry, my writing is bad. Your A ds, something like that lah. So then this is your I. So then you can see that your J dV becomes I ds. So they're kind of equivalent lah. But most likely you probably will need this one. Most likely, if you do need to manually integrate for the magnetic field, you need this one. Yeah. So I guess to illustrate with an example, right, this is one of the simplest ones, and you probably need to memorize this formula lah. So we're going to use the Biot-Savart law to find the magnetic field, magnitude, and direction due to an infinite straight wire carrying current I at distance r from the wire. So the diagram is illustrated here lah. And to do this, we just use a direct application of the law. Here, what this bulky expression represents is that, okay, firstly you have current I, right? Then we consider some point here, right? If we take this to be on the x-axis, so this entire wire lies on your plus x-axis, and this point here is your origin, right? Then let me actually take a different point somewhere here. So let's say we take this infinitesimal segment of wire here, right? And this is of length x. So then, right, what this means is that this small vector here, infinitesimal vector here, is dx times your I hat lah. So that's this part here. And your r hat is going to be, sorry, your r prime is going to be this vector here, which you should be able to see it's this lah, because obviously the component in the negative direction is, in your x direction is minus x, and your component in this direction is your plus r lah. Yeah. So then that's this. Then you can work through the math. I'll let you do it yourself. But then you eventually get uh this entire expression here, and you can see that it points in the k direction, which means if we look here and we take, oh my god, if we look here and we take this direction to be the plus y direction, right, then the direction of the magnetic field actually points out of the page, and we would denote that with this symbol lah. And this is out of the page lah. Don't mind my handwriting, I'm using a mouse. And this means into the page lah. But yeah, so basically the magnetic field here is directed out of the page, and because that's the z direction lah. And you can calculate this integral yourself. It's not too difficult. You just need a trigonometric substitution. I'll not evaluate it here, but it's not too difficult. And you can get that equal to this. So then you actually get that your magnetic field is this star. So basically, right, the most important thing you should remember in this example is just how to use the Biot-Savart law as well as this formula. This formula, you'll use it a lot. And later on, I'll present a few formulas that you should ideally memorize because those are very useful. But you should also probably know how to derive them in case in competition you might need to rederive it again if like they don't think it's like an essential formula that can be memorized. But I'll let you figure that out yourself because it's mainly just a basic application of this law again in some integration. So what this basically says is that your magnetic field from a wire looks something like this. So the magnitude is given by this mu naught I over 2 pi r, and your direction can be determined like this. If you have a current here, then if you look at the diagram if you point your thumb upwards and you curl your right hand, then your other fingers are going to point in the direction of current. Yeah. So that's the so-called right hand rule, which is kind of very helpful, especially to calculate directions of magnetic fields. And yeah, I think you should have learned. I'm not too sure what the syllabus is, but I think you should have learned this, I think. Yeah. But anyway, that's the Biot-Savart's law. And there's another form of the Biot-Savart's law, which is this. Instead of a steady current, as mentioned just now, right, this is the case of a moving charge, actually. So if we have a moving charge, let's say it's plus q and something like this, then it actually also generates its own magnetic field. Like, yeah. And I guess it kind of makes sense with wires because, again, as I mentioned previously, wires are also moving electrons, and they generate their own magnetic fields. So this is the alternative form of the Biot-Savart law in that case, where this time instead of integrating, right, you only have one point charge q, you take its velocity and you cross the r hat again, and the r hat obviously is the same as I mentioned just now. This is your r hat. It's a position vector to the point you're considering from the point charge, and then you divide by this distance cubed. It's the similar to just now. Yeah, that's the second form of Biot-Savart law. And here I give another example, but I think it should be pretty straightforward. It's just a straightforward application of the law. Basically, you have an electron that moves in this direction when your x is in this direction. So then you just directly apply the law as I mentioned just now. Yeah. So that's the Biot-Savart law. I don't think I have much to talk about this again. And okay, in this example, I guess you can also note that the directions of the magnetic field are both in the k direction. Reason being that in the first example, we had a current moving in the positive x direction. In the second example, we had an electron moving in the negative x direction. And I mean, that's kind of how conventional current works, because they're defined in the opposite direction to the electron flow. And yeah, that's just one small thing to note. Okay, so that's Biot-Savart's law. I know it looks intimidating, but again, it's really just integration lah, and yeah. Okay, next is Ampere's law and Gauss's law for magnetism. This Biot-Savart's law can get really annoying, especially when you need to do a lot of integration. Sometimes in very symmetric situations, you can apply these two laws that I've mentioned to actually calculate the magnetic field in easier ways. And this first one is called Ampere's law. Basically, it involves some closed loop, and the proof requires a bit of calculus, which we will not cover lah. But basically, this law says that, let's say you have some currents or whatever lah in free space or something like that. Basically, Ampere's law states that, actually I'll just use one current. Let's say you consider some loop in space, okay, and this loop is a closed loop, okay. So I think it should be obvious what closed means. It basically starts and ends at the same point. So you consider some closed loop, and what we are gonna do is we take this integral. What this funny symbol is, it's just a contour integral, but it basically just means that you're integrating over this closed loop in space lah. So, and the thing that we're integrating is this quantity here, which is your magnetic field dot your dl, and this dl is basically just like a differential element of the loop lah. So I guess to illustrate, if you're considering this segment right here, right, your dl is gonna be this, yeah, so that's a dl, and your b is, okay, for b, for your wire, it's gonna look something like that. It's gonna point in this direction. I guess you could also define dl to be in the opposite direction. It really depends on what direction you define them lah. But ideally you want to define them in the same direction, or ideally you wouldn't really care because you know about the symmetry of the situation, you only need a magnitude, something like that. Okay, but regardless, right, this is the integral lah. Basically we take the dot product between both of these quantities and we sum them up over the entire loop. And what Ampere's law states is that this actually equals to this quantity here. Here again we have the permissivity of free space, and here we have I enclosed. I enclosed means basically whatever this surface is enclosing lah. So as you can see, this loop, right, has some surface on the loop, right, like something like this, and you can see that this charge actually passes through this loop. Sorry, this current passes through this loop, right? So this current contributes to your I enclosed lah, basically. And that's your Ampere's law. Yeah, if any of that seemed confusing, again, we'll illustrate with an example later. I think it should make everything clearer for you. But that's Ampere's law of yeah, that's Ampere's law, yes. And the next thing I'll go through is the Gauss's law of magnetism. This is, if you know Gauss's law for like electricity, right? I guess to recap, right? Let's say you have a charge plus Q like this, and we consider some closed surface around this charge Q. This is gonna emit its own electric field, something like this, and it's gonna have some flux on this surface, right? Where, remember, we define our flux to be this, which basically means you have some small area element on this surface, right? So this is a closed surface lah, so you can think something like a sphere or something like that. This is your dA. Your dA, this dA is what we call a differential area vector, and the area vector basically is just a vector, an area vector corresponding to some surface, some small like surface, right, is a vector where its magnitude is sort of the area, right? So basically this magnitude, which is dA, would be the actual area of this small part, and its direction here is actually facing out the surface lah. So that's the area vector, right? And you take it and you dot product the electric field, which for this charge is also pointing in the same direction, something like that, right? But basically Gauss's law for electricity would say that this integral here is equals to Q over epsilon naught. And here your epsilon naught is the permittivity of free space. So this is your Gauss's law for electricity lah. What the Gauss's law for magnetism says, right, is that on the contrary, right, okay, here is used ds but it means the same as dA there, but Gauss's law for magnetism says that this integral is actually 0. So what that essentially means is, like I reiterated at the start, right? There's basically no sources or sinks in magnetism lah, sort of. But that's kind of what it means. Basically, through any surface, right? If you have basically through any closed surface, the magnetic flux through it, the net magnetic flux through it is zero lah. And that's what Gauss's law of magnetism says. Yes. So basically, those are the two laws that I have mentioned, and they can be quite useful in symmetric situations if you need to calculate the magnetic field without using like Biot-Savart's law, which can get really annoying. So I guess let's try to illustrate with an example again. And I'm going to use the exact same example as just now, but instead of using Biot-Savart law, we want to use both these laws to calculate without any integration. Yeah. So using Ampere's law and Gauss's law for magnetism, we want to find the magnetic field this time. But let's say we also don't know the direction yet. So how will we go about this? The one thing to know is that a wire is quite symmetric. It's clearly rotationally symmetric. So we can use that to our advantage. So what we first do is, let's first argue that the radial component should be zero. That means that for your wire, it will be tangential, which is basically what we had proven just now. But let's say we don't know that first, and let's say there is some radial component first. Okay, and it's illustrated here. So let's suppose that the magnetic field has some radial component BR pointing outwards. And by rotational symmetry, as I mentioned just now, right, since it shouldn't really matter which direction you look at it, because your wire is rotationally symmetric. So your radial component at any point around the wire at this distance r will have the same radial component BR, as you can see in the diagram here also. So let's start to take this Gaussian surface as is drawn here. This Gaussian surface is this cylinder, right? And we want to consider the net magnetic flux through it. So the first thing we do is we consider the magnetic flux through this curved surface, which by the logic I just mentioned just now, right, the magnetic flux is going to be this expression here. This is your BR is the radial components. Your BR is the radial component of your the radial component of your magnetic field at this distance. And this 2 pi RH is the area of this surface, because we got to remember that we are integrating over the area. And here, because of rotational symmetry and your area vector at any point also points in the same direction as the magnetic field, which is radially. So this is going to be your integral of over the curved surface at least. So that's one integral down. Then the next thing we need to find is the integral of the magnetic field on each of these surfaces. And to do that, this time we use translational symmetry, because another symmetry of the wire is that we can also move it up and down, and it doesn't really change because the wire we're considering here is infinite. So in that case, right, because of translational symmetry, sorry, water. Okay, sorry. So by translational symmetry, your magnetic field at each point on the top surface is going to be the same as that in the bottom surface, right? So if let's say we had some magnetic field that pointed like this here, because the wire is translationally symmetric, there'd be one like this here also. And you would say the same for any other point on the cylinder, like on these two faces. Yeah. So then, right, what we can then conclude is that these two integrals are actually negative. Reason being that in one case here, right, this area vector actually points outwards like this. However, this differential area vector, I'll denote ds. However, in this other surface here, right, your area vector points outward like this, right? So when you take the dot product in both these cases, right, they're going to be the negatives. And we already showed that the magnetic fields, like, on each surface point in the same direction, but your area vectors are in the opposite direction. So your integrals are going to evaluate to be the negative of each other. So yeah, now we have this relation, right? And we have the magnetic flux through each surface. So to find the magnetic flux over the entire closed surface, which is this Gaussian surface, right, we just sum all of these integrals up, and we find that both of these will cancel because of this, so these will become 0, and this integral, as we evaluated just now, is this lah. And again, by Gauss's law of magnetism, right, we've already shown, it's just the law that this integral is equals to 0, right? That must imply that this here is also 0. So by the Gauss's law of magnetism, this just necessitates that the radial component has to be 0. Because if it weren't, right, there's no net magnetic flux through both these surfaces. And if there was a radial component, then there'd be a net magnetic a net magnetic flux out of the cylinder lah, which is bad, and that kind of violates Gauss's law of magnetism. So that means that our radial component is 0, and we have argued that this magnetic field should point tangentially. And that was kind of the hard part. Now we get to the easy part, right? So now we have it points tangentially. So this time we consider a circular loop of radius r around the wire, and we choose the direction of integration to be dictated by like the right hand rule we introduced just now. And we suppose that the magnitude here is b. Then we use Ampere's law this time, right? So using Ampere's law, right, we're going to integrate the magnetic field over the length. And you can realize that these two vectors point in the same direction now. And your b has the same magnitude overall. So you can find that this integral is just going to be 2 pi r b lah, because your 2 pi r comes from the fact that that's just the length of this entire loop, and your b is just b. So then from there, we now get that b is mu naught I over 2 pi r, which if you go back to our previous example where we integrated using Biot-Savart's law, it's the same. So we retrieve back our result from just now lah. Yeah, and that's basically just an example of how to use Ampere's law as well as Gauss's law for magnetism to like calculate magnetic fields in symmetric situations lah. And yeah, okay, most of the time you probably don't really need Gauss's law of magnetism, because as long as you have the intuition that a current produces magnetic fields that is dictated by the right hand rule, right, then you probably don't really need this. And sometimes it can be pretty obvious where it points. So for example, right, if let's say we had a circular loop of current instead, right, and you wanted to determine the magnitude of you wanted to determine the magnetic field at the center, right, you know that because if you consider this small infinitesimal segment here, right, this will generate its own magnetic field that's pointing downward into the page, as guaranteed by right hand rule. And you can also argue the exact same for every other infinitesimal element along this wire lah. Then that would just mean that your current here points out into the loop lah. And here you didn't need to use any Gauss's law of magnetism or whatever, and you immediately get the direction, which helps a lot lah. Yeah, and Ampere's law usually will set them to rest, or you can use Biot-Savart's law. Yeah. And yeah, so those were the main laws that you usually would use to calculate magnetic fields. And just one thing to bring up, right, which is the concept about conservative fields. Basically, conservative fields, I don't really know how to explain it, but it basically just means that if you have some vector field in some space, right, if you say you take two paths within this space, right, we denoted A and B, and you calculate this integral here, your v dot dl. Oh wait, sorry, you don't take 2 points, you take a closed loop, my bad. You take a closed loop and you calculate this integral. This integral is actually equal to 0. This is the condition of being conservative. And if you want to relate it back to another example, such as mechanics, that basically just means that when you go like here and back, your work done, for example, if this field, right, this is not velocity, this is a vector field, but if this meant force, right, then what this integral means is actually would be a work done, and what that means is that your work done to come back here is 0 lah. Yeah, so Basically, that is what means to be a conservative field, and usually that lets us make this thing called a potential energy function lah, where because your potential energy is a state function, which means that it only depends on the position. And to calculate, like for example in mechanics, if we were to calculate the work done to get from here to here, we would just like take the difference in potential energies, something like that. Yeah. The funny part about magnetic fields is that they're actually non-conservative because by Ampere's law, we've already stated that this integral is this stuff. So actually, magnetic fields are non-conservative, which can make them a little bit weird. But I think most of the time you don't really need to worry about it. It just means you cannot really define like a potential energy to the magnetic field per se in that traditional sense, where you can define a potential energy for like a force, because you can you can differentiate the you can sort of take the derivative of the potential energy you get force. You don't even know what this symbol means. It kind of just means your derivative, kind of. But you can't really do that for magnetic fields. So you don't really have an associated magnetic energy per se. But you don't really have to think too hard about this. It just means that it's a little bit weird. But yeah, you don't really have to think too hard about it. And okay, now that I've introduced the laws, here are a few common results that you should probably remember. I would say this, 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 maybe this, I don't really know. But these are probably more important to memorize. But yeah, these are probably more important to memorize. But you can derive this by yourself using either Biot-Savart's law or Ampere's law, and these are just useful results to memorize lah. And I won't elaborate too much. I'll just leave it to you to evaluate it yourself because it's not too difficult. But it's a good practice lah. If you want to practice your use of both of these laws, if you want, you can send me a solution. I can check it if you want. But yeah, and yes, sorry. But yeah, these are just some common results that you can derive yourself, and it's good to memorize. This gives you the magnetic field magnitude at these points. You can look at it yourself later. I won't go too much into it. And this is just a small example which applies the formulas, but you can read that yourself. It's not too deep. It's just a square loop like this, and you want to find the magnetic field at the center. But we have this formula here for a finite straight wire carrying steady current, and you can get a magnetic field. One thing to mention is that finite wires actually cannot carry steady currents on their own. They usually either need to be infinite or they need to be connected to some voltage source or something like that. But how this particular example works is that we use the concept of superposition solve, where we can superimpose setups. So basically, how we calculate the magnetic field here is that we sort of consider one wire first of steady current I. It doesn't really exist per se, but if it did exist, then we have some magnetic field here. Then we sort of add the contribution by this, contribution by this, and contribution by like this. And in that way, you get a closed loop which can carry a steady current. And so the configuration is technically valid. And you can calculate the magnetic field here by just summing them up. But you probably also don't have to think about this too much. Superposition basically just means you can add the magnetic field from multiple configurations. Yeah, it's not too deep. So with that, we've come to the end of the first part, which is about the laws that can be used to calculate magnetic fields. Does anyone have any questions at this juncture? Okay, I'm gonna assume not. If so, then I'm gonna proceed, because I realized I'm taking a little longer than I thought. Maybe that's a good thing, but I don't know. Yeah. So, okay, next thing to start talking about is magnetic dipoles. These are actually kind of important usually. You know, because traditionally when we think about magnets, right, they usually have a north and south pole, something like that. They have their own magnetic fields around them, and again we have that the like poles they will repel and the opposite unlike poles will attract, something like that. I don't know how to draw it, something like this. Yeah, but yeah, basically your magnets can sort of be modeled as magnetic dipoles if they're small enough. But your magnetic dipole is basically sort of like a traditional bar magnet that you think about lah, but small. But to illustrate it better, I also used an example. To be fair, I have a lot of illustrations by example, but I think it will help. So basically, a magnetic dipole is similar to that of an electric dipole, which we introduced in one of the previous chapters, where if you have some two small charges that are close together, they sort of exert this field that looks something like, I can't remember how to draw it. Something like this. I'm not drawing it very well, but like it will look something like that. This is your sort of an electric dipole. Yes. A magnetic dipole is similar to an electric dipole, in which it has a similar field configuration around it, something like this. But to illustrate that, I'll use an example first, which is we use a circular loop of wire. I won't go too much into the derivation itself, although I'll point out a few things. So basically we have this circular loop of wire, right? And let me draw it out over here because I didn't provide a diagram with the axes, but this is X, this is Y, and this is Z. So basically what we're considering is that we have some circular loop of wire of radius R, right? So something like this. And it lies in the XZ plane, so it's like this. And it current points anti-clockwise when viewed from the plus Y axis. So it looks something like this, because we're viewing from the minus axis this time. But yeah. So what we're going to be doing is we're going to be finding the magnitude of the magnetic field at some point on the x-axis here and some point on the y-axis here. So to do that, I won't go too much into the details, but the second part should be easier, and I think you should already realize that that's basically this formula where you have a circular wire loop and you just get this quite easily. This is your direct application of the formula. And we get from here to here because the main thing we're assuming in this question is that this wire is super small. And if it's super small, that means these dimensions x and y are much greater compared to, yeah, these distances are much greater compared to this small distance lah. So yeah, if we apply this, right, we can sort of approximate this as this because your y is much bigger, and you get this equation lah. And this is a more, where it's on the x-axis, it gets a little difficult because you need to use Biot-Savart's law this time. I'm not too sure if you can do it by amperes, but I think the easiest way is by Biot-Savart's. But when you directly apply it, you get this really tricky integral, which you have to evaluate. But you can exploit the fact that your x is really big, and you can sort of do a Lorentz series expansion that looks something like this. I'll just gloss over the details, but then eventually you get to here, and you get this integral which is really simple to evaluate, and you get this expression lah. I'll not talk too much about this. You can read this example yourself, but yeah. Basically what this example is trying to illustrate is that if you remember from a previous chapter, it should have been derived that if you have some dipole, which I'll illustrate with an arrow here with its electric dipole moment P, right? And you want to calculate the on-axis and off-axis electric fields, right? Then you have expressions that kind of look something like this, where they are sort of in the ratio of 1 to 2. Yeah. This example is trying to illustrate that this behavior is also exhibited in magnetic dipoles lah, because the notion of the magnetic dipole here we're going to consider, which is an Amperian dipole for information. Basically, you take this dipole and you take this loop and you shrink it as small as possible, and you get a magnetic dipole lah. So you'd have a magnetic dipole moment m that's analogous to this electric dipole moment, and this magnetic dipole also generates a field that looks similar lah. Something like that. I draw it really badly. like this dipole also generates its own magnetic field that looks very similar to the one of the electric dipole. And it has its own magnetic moment, which we define by IA, where I is the current, this A is the area vector as I mentioned just now. So if you had the loop of wire, something like this, then your magnetic moment, here your area vector actually points in the direction that's detected by right hand rule. So here it would be pointing downwards. This would be your area vector. And this I is just going to be the I here. And again, this direction is detected by the right hand rule. So this is what we define the magnetic moment of this loop to be. And in general, if you have some arbitrary loop, you can also define the magnetic moment similarly. And for a solenoid where you have multiple loops, right, you just multiply by this and this n lah. Yeah. And that's the number of turns of the solenoid, something like that. Yeah. So basically that's the notion of a magnetic dipole. And it turns out that as we derived previously here, as well as previously derived in the previous electrostatics chapter, right? You have this perpendicular and parallel formulas for the magnetic field, and they take on this formula and where this m is your dipole moment. Yeah, so that's sort of the notion of a dipole. And with dipoles, they also come with torque and potential energy, because this is also very similar to those of the electric dipole, where the formulas look something like this. U equals to this. So basically it's kind of similar for a magnetic dipole. These are similar expressions, so I'll not talk about them too much. And it also seems a little unusual that we have a potential energy in this case, but that only really applies to dipoles, yeah, it doesn't really apply in general, but basically sometimes this potential energy can be used to find forces, as I'll show in a future example later lah. But for now, just know that you can calculate the torque and potential energy of a magnetic dipole, something like this as well. Yeah, that's just an introduction to magnetic dipoles, and I'll talk about it better later. Yes. So now we're done with the magnetostatics part. Now I'll be talking about the magnetic forces. So we've talked a lot about the fields that are generated by currents and charges, but obviously these fields also come with their own forces, similar to electric force, but it doesn't take on exactly the same formula lah. But yes. So anyway, first we have the magnetic force. Okay. So let's say we have some magnetic field in some space. So let's say we have a wire again, and with the wire we have some magnetic field like this. And let's say we had some charge moving quite near this wire, so it's in the influence of this magnetic field at some velocity v. What the magnetic force that acts on this charge is dictated by this. It's a little bit weird, because for the electric field, for the electric force is defined just with your charge in your electric field. And it's kind of similar to your Newton's second law, where your force acting on something is the mass times the acceleration. And your electric force is similarly the charge multiplied by the electric field. But here your magnetic force takes more foreign expression, where this time it actually also takes into account the velocity. So here, right, the magnetic force is calculated with your velocity and your magnetic field, where you actually take the cross product. So your force actually acts perpendicularly to both the magnetic field and the velocity. This sounds very weird, and to be fair, it kind of is. That's just kind of how physics works. But the magnetic force is a really weird thing, and we'll later show that actually this implies something very useful sometimes, which is that the work done by the magnetic force is actually zero. But we'll show that later. This is the magnetic force, and this example, I guess I can get you to read that yourself, but basically we're just considering a point charge that moves in the xz plane as p of v in the x direction, and then there's a magnetic field that is switched on in this direction, and what we want to do is determine the motion of the charge. This is usually very useful because, okay, actually, let me use the y direction to be something like this. This is actually very useful because actually the path of the charge inside is a circle lah. I'll not go through the math too in detail, but if you just simply use Newton's second law, ma equals to qpp, and you get this, right? And you just consider the direction of the cross product properly, you get that the magnetic force, firstly, it doesn't do any work because it's pointing perpendicularly, and secondly, your kinetic energy is always the same. Secondly, that implies that your kinetic energy is the same, your speed remains the same, your acceleration has constant magnitude, and it always points perpendicularly to the velocity, so your charge actually undergoes circular motion lah. So your charge would go something like this lah. And this is very useful in a lot of practical applications actually. And these formulas are kind of useful to memorize. If you just equate the acceleration to if you equate the centripetal acceleration to this acceleration, right, you can get this, which is the radius of your orbit lah, because your charge will orbit inside the magnetic field, and this is often called the cyclotron radius. And there is also an associated angular frequency which you can calculate in a similar manner, which is like this, and this is also often termed the cyclotron frequency. And these expressions are definitely very useful to memorize. You are probably going to use them a lot. You're probably going to use them at least once in SPhO. Yeah, these expressions are pretty useful. But I'll let you do the math and read yourself lah. Yeah. And yeah. So now we'll consider currents instead. Okay. So currents, right? Currents, they are also consisting of moving electrons lah. So each of those electrons are going to experience some force. Because of that, your whole wire is going to experience some force lah. And if you do the math again here, right, your differential force is just differential charge times this. You can equate this to be this, and then your dt times v is just this small dl here lah. And you can actually get that your force that acts on a wire can be determined by this integral here, which basically just means that you just integrate this expression lah, your dl, as I mentioned just now, how it's defined, multiplied by your p lah. Like cross product your p. Yeah, your p would probably be pointing something like this, and then it exerts some force. And if let's say it was in a uniform external magnetic field, so your magnetic field is just the same everywhere, and if your wire carries a uniform current, then you're probably going to use this formula more. Is your F is IL cross B lah, and this is the magnetic force that acts on a wire with uniform current and uniform external magnetic field lah. This will be useful for you, yes. And here's another example. I'll also gloss because it's kind of easy math, but basically if we have two currents, I1, I2, like this, and we want to calculate the magnetic force between the wires, we just gotta note that this first wire has its own magnetic field around it, right? And it's going to pass through this wire, something like that, right? So there's some magnetic field acting at the position of the wire, which generates its own magnetic force that's governed like this. So you can just work through the math yourself, and you get that the magnetic force per unit length between these two wires is this. This is another formula that's useful to memorize. A lot of these formulas are pretty easy to memorize. And actually the derivation you can memorize also, because if you need to derive it on the spot again, because it's not too difficult. And if you consider the directions more carefully, which is not here in the example, but if you consider the directions, you actually get that these currents will actually attract because the currents point in the same direction. And likewise, for an opposite case where your currents point in opposite directions, your wires are actually going to repel. That's if you consider the directions more carefully, and that's also a good thing to know. Yeah, that's just another example of something you should memorize. Okay, next we're going to the Lorentz force, which, although it sounds very fancy, it's basically just the electric and magnetic force together. Here you can see this component is by the electric force, and here's the component by the magnetic force. So it's basically an electromagnetic force, and we term it the Lorentz force. Yeah. Here is a long example where basically we have an electric field pointing in the x direction, and we have a magnetic field pointing in the y direction. Yep. So we have an, actually I'll just draw them directly. We have, yeah, we have the E pointing here, and we have a B pointing here, and we release some charged particle from rest, and we want to calculate the motion. We want to calculate the motion of the charge through this here, and it requires a bit of solving of differential equations. Again, I'll leave you to read the math again, but you just use Newton's second law. You can decompose the components, and it looks kind of scary to solve this couple of differential equations, but actually all you need to do is you differentiate one of them. You differentiate one of them, you get here, you substitute into the other one, and then you actually just get simple harmonic motion for one of the velocities. Your other velocity is also kind of simple harmonic motion. You can integrate both of them to then get these results. And one thing I want to point out about this is that even though your electric field points in this direction and your magnetic field points in this direction, right? Your direction of your average velocity of the charged particle in this field is actually pointing in this direction. And that actually doesn't depend on your charge, as you can see, because here, right, after you derive everything, you get that Z is E over BT, and this doesn't depend on the charge. So it seems counterintuitive because your electric field should tend to divert your charge in this direction, but because of your magnetic field, it sort of twirls into a really weird shape. Yeah, and this is what we term the E cross B drift. Yeah, and another thing that is kind of goofy is that if we actually go into a frame that's moving at this average speed in this upward velocity, right, and if you went into this frame, right, your charge is going to be observed as moving in a circle, actually, because clearly if you get rid of this T, right, then, and you also kind of ignore this X, doesn't really matter, it looks like a circular motion. Yeah, and it's sort of out of scope to explain, but you can sort of explain the concept of field transformations in where if you move in a frame, your electric and magnetic fields may actually change. So in this frame moving with the drift velocity, right, your electric field actually becomes zero, and your force is basically purely magnetic, which causes this orbit in this frame lah, which is what I mentioned about just now. So it's a bit out of scope, but that's just something to know. It's actually just your motion is just gonna look something like a helix because your thing is moving. Not helix. I think it's a cycloid, something like that. But if you went in that frame, it's gonna look like a circle lah. Yeah. So that's just an example to actually use Lorentz force. You can read through the math yourself. It's a bit complicated, but I'm not gonna talk too much about it anymore. Yeah. Okay, now I'm gonna briefly cover a few applications. It's not gonna be too deep. You can mostly read these parts yourself, but because I need to get to the next section soon. But basically, two important applications are velocity selectors and the Hall effect. Okay, so selectors basically use the electric fields and magnetic fields to sort of filter speeds lah, kind of. So if you consider do I have an example here? I have an example, it's a bit different, but okay, but basically for a velocity selector, how it kind of works is that we have charge plates here, one positive and one negative, right? And this creates a uniform electric field E inside it. Okay. On the other hand, we have another, perhaps like two magnets outside or something like that, but it generates a uniform magnetic field B, something like this. Yeah. So how the velocity selector works is that we take like charged particles, right, and we shoot it through at some velocity. What the velocity selector is going to do is that only particles of some certain speed are going to be moving in remain undeflected, so they're going to keep traveling in a straight line. If it's too slow, it might deflect in one direction. If it's too fast, it might deflect the other direction, etc. But you can do the math yourself where you consider the Lorentz force again, E plus V cross B. You can just do a bit of calculations. You consider directions, and you get that the velocity sector speed is this, which you actually notice is the same as this. But I digress. So you can work through you can think about the directions yourself, and you can just think about how the velocity sector works by itself. It's not too difficult to understand that, but basically the electric force and the magnetic force will cancel each other out for the perfect speed because your magnetic force depends on the speed. So that's how velocity selectors work. And there will be a few questions later on velocity selectors because they require a basic understanding of them. So yeah, that's a velocity selector. Here's another example. I'll just leave it to read. I'll just leave you to read this yourself. It's not that difficult of a concept. It's similar to a velocity selector, except this time you need an extra centripetal acceleration. The Hall effect is something where your currents can potential differences can be created across conductors if they have a current through them as well as a magnetic field. As you can see in this example here, let's suppose we have a current that's flowing through here and we consider an electron. It seems to be moving in the wrong direction here, but your current should be pointing in this direction, I believe. If this electron will be pointing like this, but anyway, if your electron moves, it's in the conductor travels along the direction of it travels along the direction of the current for the electron. It travels opposite the convention current and has some velocity which is called the drift velocity v. And what we want to do is we find the potential difference across the conductor as well as where. The reason there's a potential difference is that basically if you consider the electron here, right, it has this velocity here and it has this magnetic field that's pointing out here. You can consider your cross products carefully, which I am thinking about now, and you get that your force acts in this direction because your charge is negative. So your force will act in this direction, and that will actually cause a buildup of electrons here and a buildup of positive charges here. Yeah. Okay, if my direction is wrong, forgive me, but either way, the point is that these two surfaces are going to be charged, and that will create some opposing electric field, something like this, because of the buildup of charges on these surfaces. And that has its own associated potential difference with it. And at some point, once enough charge is built up, right, this electric field is going to be big enough such that it exactly opposes the force by the magnetic force. So like this. So once this has built up enough, your electric force is going to balance the magnetic force, and any subsequent electrons that travel like this will remain undeflected, which is exactly the concept of the velocity selector I mentioned just now in a similar aspect. But yeah, that's sort of how the Hall effect works, and you can calculate it yourself, but then you can get this expression for the voltage between the two because using the velocity selector formula, your E is the voltage over the thickness, which is here. That's by a capacitor. And then you divide by B of V voltage is this, and that's this term, your Hall voltage. That's just one application of the forces. Yeah. Those are some brief applications. And one more thing I need to elaborate on are magnetic dipoles again, because to calculate forces, the magnetic forces on magnetic dipoles, it can seem a little difficult, but okay, it can seem a little difficult, but actually we can just use the potential energy as we had mentioned just now. This potential energy is the potential energy of a magnetic dipole, and it turns out that we can differentiate it in the respective directions in a similar way to get forces that act on the dipole. So to go through this example from Griffiths, we have two permanent magnets that can be treated as dipoles, and one of them levitates above the other because of the magnetic force acted on by the other one. And we're asking at what height does it float? So how we go about doing this is that the first thing we do is that we consider the magnetic field due to this bottom magnet at the top one lah. And this is from what we derived just now lah. From a dipole, we have a magnetic dipole like with some magnetic moment, and we want to calculate the magnetic field along parallel at the displacement that's parallel to the magnetic moment. And we can go back to our calculations just now and we can compare, and we actually get that this is the formula lah. Yeah. Usually if they dealt with dipoles, they probably give you the formula, I think. But yeah, this is the formula for the magnetic field at a displacement that's parallel to this magnetic moment. And yeah, so then using this formula, we can then get the magnetic potential energy. I'll let you to read more carefully, but this is your magnetic potential energy and it's positive. So what we can then do with this magnetic potential energy is we then just differentiate it with respect to the distance z, right? And we actually get the force that interacts with this magnet lah. This is your FB. So once you differentiate it, this is our force by the magnetic. This is our magnetic force by the dipole. And all we need to do is we equate it to the mass. We equate it to the weight of the magnet, and we can just get the height lah. So that's just one simple illustration of how we can use the magnetic potential energy to calculate force lah. Yeah. So any questions at this juncture? Quickly. Water. I assume not. Okay, I'll go into the last section now, which might be more important, but I'm going to present some ideas for solving some problems. So the first one is conservation laws. Oh, I received it. Go through Gilbert dipoles. I'll be going through them in a bit. Yes, trust me. I'll go through them later. Yes, trust me. Okay. So, first thing I'll be talking about is conservation laws. Okay. So, as I mentioned just now, right, if you use the formula for the magnetic force, right, and you calculate the work done, since the force is actually perpendicular to the velocity, you actually get that the work done by the magnetic force is always zero. And this arises since the cross product is perpendicular to both of them, blah, blah, blah. The dot product is zero, blah, blah, blah. So, in the absence of other forces, the kinetic energy of a charge is conserved by the work energy theorem, actually. So, below we have an example from SPhO 2024 as adapted, but this is actually very worth understanding lah. So I'm gonna go through this a little bit in depth. Okay. So the problem is that we have a wire that points in this direction, and we have an electron that is projected. That's projected with some initial velocity v naught, and it is perpendicular to the wire. So the question basically asks you to find the maximum and minimum distances that this electron will achieve from the wire, because it will probably look something like this, the path, something like that. I don't know, but it really doesn't matter. What they want us to find is not the entire trajectory or how it depends on the time. They just want to find the maximum and minimum distances y max and y min. So it seems pretty difficult because your first instinct would probably be to solve a differential equation using Newton's second law. But that is a really terrible idea. And sometimes there are some shortcuts which we can apply. So the first thing we do is we consider Newton's law in the x direction first, but we're not going to integrate anything. If we consider it and we consider the forces carefully, which I'll let you figure that out, you get that this equation is true. And if we use the fact that this is the derivative of vx and this is the derivative of y, you get this equation here. The bad part about this equation is it's a bit difficult to solve along with the other Newton's second law in the y direction. The good thing about it is that if we treat our infinitesimals as if we treat derivatives as fractions of infinitesimals, which we can kind of do, we can actually get rid of this dt here. The reason we want to get rid of this dt is because nowhere in the question they've asked anything about time, right? So a good thing to do is just to get rid of it here. And the good thing about this particular equation is that we can determine our vx, as we show later, And this y, right, is what we want to find. We want to find the minimum and maximum distances. So we can get rid of the dt, right, and we can actually get this equation here. We eliminate the time dependence, right? And after a bit of integration, right, you eventually arrive at this. So you actually get an equation for your y, which is the perpendicular distance to the wire, in terms of its horizontal velocity. So now all that we're left to do is just to determine the horizontal velocity, right? But the main thing here is that we want to use the conservation of energy, right? And in fact, how we use the conservation of energy is that there's no loss in energy, in kinetic energy, right? Because the work done is zero. What that must mean is that throughout this entire trajectory, right, your speed is going to be constant. That makes sense, right? Because again, the work done is zero, so your speed has to remain constant. Your kinetic energy is constant throughout the entire trajectory. So when we have our maximum and minimum distances, right, again, I'll let you consider directions properly, but when you have the maximum distance, right, your velocity is going to look something like this. And your this velocity is v naught because the speed is always constant. And in the opposite direction, where it's minimum, it's going to look something like this, where your v naught points in the opposite direction. And the reason that there is no radial component like this is because if there was a radial component like this, then it wouldn't be an absolute maximum. And the same thing with this lah. It should be pretty easy to see lah. Yeah. But so now we have the information that at the maximum and minimum distances, our x velocities are plus minus v naught respectively. And you can just consider the direction of force yourself. And we can solve for the maximum and minimum distances as this. So we turn a problem that initially looks very intimidating, that we have to solve for the trajectories, to a very simple problem where all we did was just plug in the horizon. All we did was just plug in the speed. And this is an idea that is very useful for especially harder competitions. And this actually comes out quite often. Yeah. So the conservation of energy and the constraint equation implied in the problem statement. Usually both of these together, they can be quite useful, especially if you don't need time and you can try to eliminate it. Okay, next we're gonna get into magnetic monopoles. So just now, okay, this is a little bit tricky to say. Basically, just now we talked about Gauss's law of magnetism, which basically says that there are no magnetic charges. So I got a question. Why is there a force in the xy direction? Because here, right, okay, in this case, right, you have your current pointing in the minus x direction, right? If you use your right hand rule, literally just point your thumb in that direction, you curl your fingers, right? Your magnetic field points inwards, illustrated here, right? If your velocity always lies in the xy plane, right? Let's say your velocity is something like this. Let's say it's something like this, right? If you take the cross product, your cross product is also going to lie on this plane, right? So there's going to be an x component and a y component, but no z component. That makes sense, right? Yeah, it's the same force, but these are the decomposed forces. These are the decomposed components, yeah. Okay. Anyway, what was that? So previously we talked about Gauss's law of magnetism, which states that the magnetic flux through any closed surface is actually zero. This basically just means that no magnetic sources or sinks, which for the electric analogy, there are sources and sinks. This would be a source because the electric fields come out from it, right? But this would be a sink because electric fields enter into it. And what this law basically says is that for magnetic fields, that can never be the case, because it's always to describe it in one word, it always be rotational kind of. Yeah, your magnetic fields are always rotational in that sense. What magnetic monopoles say is that actually they're not, because magnetic monopoles are sort of a hypothetical concept where instead we introduce magnetic charges, sort of, because actually electricity and magnetism are sort of the same things. So we can sort of define these similar quantities. Just now we have already presented a lot of analogies between. Just now we've already illustrated a lot of analogies between these like two counterparts, your electric dipoles and magnetic dipoles. And similarly, a lot of these electricity and magnetism have their own analogies. So in this case, although it's hypothetical, it is possible to define a sort of magnetic charge. And these magnetic charges, right, they emit magnetic field radially. Obviously, right, the thing to know is that this can never actually happen in real life. Right? This can never happen in real life. Okay, you know what, I give up writing it, but you get the point that this will never actually happen in real life. But we saw some questions usually they deal with these hypothetical magnetic charges. So if they do, the good thing to know is that they are very, very similar to the electric analogies, where basically your 1 over 4 pi epsilon naught, this is your electric constant, that would correspond to mu naught over 4 pi. And we have other basic quantities like E would correspond to B, P would correspond to P would correspond to M. And here your charge Q would correspond to this Qm. And this Qm is what we deem a magnetic charge, which has units of ampere meters. And this hypothetical magnetic charge would then have a radial magnetic field around it. This would obviously violate this Gauss's law of magnetism, which says it's zero. Because clearly, if you surround it with a sphere, right, then it's going to have some non-zero magnetic flux. But that's why we need to modify it as this lah. So instead, if you have hypothetical magnetic monopoles that exist, you would then have this equation be true instead, where instead you are considering mu naught times your Qm closer. And this is again analogous to that of the electric field, of the electricity version, where instead it would be your E dot ds, and that would be Q enclosed over epsilon naught lah. That's an analogous in a way, and that's assuming your magnetic monopoles exist. And if your magnetic monopoles exist and there were no electric fields, right, this is kind of important, but if there are no electric fields, then it'll be subjected to a force that's like this, and it also points in the same direction. It also points in the same direction to your magnetic field lah. Yeah, these hypothetical magnetic monopoles would experience. These don't usually come out very often. Probably if you participate in more difficult competitions, these could come out, but it is sometimes good to note that this analogy between electricity and magnetism always exists. So magnetic monopoles they are basically sort of similar to electric charges, but they can't actually exist in real life. But one application of magnetic monopoles that is applicable in real life is something that we'll call Gilbert dipoles, which you said you need an explanation just now, right? Yeah, but basically Gilbert dipoles, right? These have the idea that magnetic dipoles are like electric dipoles, and just now we introduced that idea and all. But with the magnetic monopole analogy, we can introduce this notion of Gilbert dipole. Previously, we said that a current loop which has some magnetic moments, right? Some magnetic moments, something like this. If we shrink it small enough, it would have a field around itself that resembles that of an electric dipole. This is the concept of an Amperian dipole, as I have mentioned just now. This is the Amperian dipole. Instead, we can also consider a dipole to be two magnetic charges like this, which will denote minus qm. I need to write it bigger. You can denote it as 1 minus qm here and 1 plus qm here. And this has its own magnetic moment like this. And this is, as you can see, it's quite clear that it's similar to that of the electricity version. But you can model a dipole like this, and it turns out that the field outside will basically be the same as that of an Amperian dipole. The only disadvantage is that the field inside this Gilbert dipole is not actually reflective of that in actual magnets. Because if you actually look at ones that are magnets, right, it probably looks something like I forgot how it looks. Something like okay, whatever, I'm too lazy, but I can't remember how it actually looks. My bad. But your inside a magnet, right? If this is enclosed inside a magnet, these will actually point in the opposite direction. And this is just to make sure that your this is just to make sure that your this is just to make sure that your Gauss's law of magnetism is satisfied lah. Because like that, now your integral will be zeros. Now it's rotational lah, basically. Yeah. If instead it was like this, then you'd have a problem with Gauss. You'd have a problem with Ampere's law. Yeah. So, but um the outside the magnetic fields inside the dipole, right? Gilbert dipoles and Amperian dipoles are basically same on the outside lah. And you can read this entire part yourself, but basically it is analogous to two magnetic charges separated by some displacement, and you define the magnetic dipole moment like this. Leave everything as an exercise to rederive the previously obtained results. We do need it, and it's indeed analogous. And we will be going, and I guess one useful example to go through is this. It's from an SPhO problem. It looks very scary. I was also very scared when I did it. To be fair, I didn't solve it because I was a bit stupid. But here we can actually use the concept of Gilbert dipoles to advantage. So I guess to explain the question clearly, right? Basically, you have spherical magnets, okay? So your magnets look something like this lah. A spherical magnet, and these spherical magnets have diameter delta and magnetic dipole moment m, so it looks something like this. And they are bound together by magnetic attraction lah, so they're attracted to each other and they form a chain like this. So what we want to do is we want to obtain an expression for the magnitude of the magnetic B field at some point P over here with the parameters R, theta, and this L. Okay, the important things are these two assumptions. The first thing is that this L is much greater than your R, and your second thing is that this distance here is much greater than the diameter lah. So they want you to find the magnetic field. It sounds very intimidating because it feels like to find the potential energy and to differentiate to get sorry. To find the magnetic field, you have to you wouldn't really know how to start, I feel like. Because you have dipoles, right? And dipoles have their own dipole field. I didn't write it in the notes here, but they have their own dipole field, which is a really complicated expression. And they have to sum that out over all the magnets. It seems very daunting lah. But one thing we can instead do is we use the notion of Gilbert dipoles. If instead we use the notion of Amperian dipoles, right, then our setup would look something like this, where we'd have many loops like this, right, etc., like this, and these all have the magnetic moment that point in this direction. And if you wanted to find the magnetic field here, you'd have to consider the magnetic field by each of these loops separately, and it'd be really weird to do so. It's not a very nice Biot-Savart's law. It's just not nice. But instead, if you use that Gilbert dipole analogy, right, basically the trick is that these magnets, right, they can sort of be treated equivalent as a Gilbert dipole with magnetic charges, something like this. And the smart thing to do here is that because we assume that all these diameters are small compared to this distance that we're considering, right? We can set the distance to be between these charges to be some finite small distance and be okay. They basically have the same field as if it was an actual like proper magnet, right? And what we're gonna do, the smart thing we do is that we actually let this d be this delta. So what actually happens is that basically this is a diagram, right? Oh, my one now is panicking. Your magnets look something like this, and they're bound together by magnetic attraction now, because your magnetic moments point like this in the same direction. The thing is that if we set this is the magnetic charges in each magnet, right? If we set the d to be delta, exactly the diameter of the magnet, right? This plus goes to the, okay, more specifically it's close to the end, but it's basically at the end, right? And these two will actually overlap with each other, because you can imagine this is a plus minus here, but there's also a plus minus here. And these two magnetic charges are at the same position. So they basically cancel each other out, right? So the overall net effect, right, is that you have one magnetic charge over here plus qm, something like this, and you have one magnetic charge over here minus qm, something like this. I mean, the other one could be positive, the other one could be negative. It doesn't really matter because they didn't specify, but we're trying to find magnitude. But basically, that reduces everything in between. That gets rid of everything in between, and we only what? That gets rid of everything in between, and we only have these two magnetic charges, right? So all that's left to do to calculate the magnetic field, since the magnetic fields by each of these magnetic monopoles have cancelled out, right? We just need to find the magnetic field by by both of these magnetic charges, and actually technically only one of them, because another assumption here we have is that this L is much greater than R, right? So this length is bound to be much more compared to this, which means that because they follow an inverse square law, this thing is going to be basically negligible compared to this law. So all we need to do is to find the magnetic field by this singular magnetic charge, which just obeys the quote-unquote Coulomb's law lah, which is this lah. But yeah, from there we've already basically obtained the magnetic field strength at this point P, which is this lah. And that's actually our answer already. We're done already, actually, because as we already mentioned just now, all the other magnetic charges have cancelled each other out, and this magnetic charge is too far out to be like significant. So we actually have our magnetic field magnitude, and we even know the direction. It's gonna be either in this direction or that direction. They didn't specify because they didn't say which direction the north or south pole is, but we know that it has to point somewhere along this line. Yeah, and that's it actually. I think that's it for the chapter. These ideas, especially the last, okay, all these three ideas are sort of more complex. In SPhO, I'm not too sure if you will need them, but if they do come out, they are definitely very useful and they can definitely help to simplify a problem a lot. And yeah, so those were the ideas for this chapter. And with that, I think we're done with the notes part of the chapter. So now I'll be going on to the problems. If anyone has any requests, I'd like you guys to point out to me right now. I don't want to go through every single problem, but if you all have done any of the problems and you want me to go through it, you please message somewhere in the chat or something like that so I can go through it. Or even if you haven't done some of the questions and you just want to know the solution, if you look at it and you don't really know how to do it, then you can ask. Okay, what if you said 213? What if you said 212? Does anyone have any of the earlier problems that they want to do? Because these are actually quite close to the end. But yeah, these two. Any other requests? If not, I'll just go through both of these. Okay, I think I'll go through both these first. I might point out a few. Actually, no, I'll also go through 2.5 also first. I think 2.3. 2.3 is a good one, I think. Because I think it was raised up to me previously, someone had done the problem. I'll go through 2.3 first, I guess. Because the rest are usually a lot of calculation bashes, and I feel like y'all should be able to do it. They're standard SPhO questions. But 2.3 looks a little more unconventional. So basically, this problem is very short. It says, show that the magnetic field on the axis at the end of a long solenoid is approximately half the magnetic field at its center. Very short, but if you don't know how to do it, it seems a bit challenging, because basically it's saying we have a super long solenoid. Let's pretend this is a really good solenoid, okay? This is a really long solenoid, right? And we have some current flowing through. I don't care about the direction, but your magnetic field is going to look something like this. Okay, pretend that they don't overlap. Let me just draw it bigger. Oh, wonder. Right. So, where did my diagram go? Sorry. Okay, the solenoid looks something like this, right?
Oh, guess what I found?
And your magnetic field looks like this, okay? So something like that. And there's obviously edge effects because the solenoid is not perfectly infinite. It's not infinite, but we're saying it's very long. So there's going to be some magnetic field at this center here, B0, and there's going to be some magnetic field at the edge of this solenoid, which we're going to call B1. And what the question asks you to do is they ask you to show that the magnetic field on the axis at the end is approximately half. So what we want to show is that B1 is approximately half of B0. Does anyone have any ideas as to how to approach this, first of all? I just want to ask you all. Like, what comes to your mind first? Just feel free to say anything. Symmetry. How exactly? How exactly do you use symmetry? Did it the long way. I think it was the one I saw. Yeah. You can also do it the long way where symmetry like it's half. Okay, I think you know what I'm talking about. I think you know what I'm thinking. For the person who did the long way, it's also technically possible, but it's very tedious lah. Because what I assume you did was you consider it as loops like this. You calculate the center using that one formula that we had, right? And then you integrate it over the entire thing. Here you integrate it over the entire thing, and you show that it's half. That's also possible, but it's very, very tedious. But actually, this is almost a one-step problem, actually. So, what I want to illustrate is that basically, yes, you can use symmetry. The first thing you need to know is that you know that your B0 is approximately mu naught and I lah. This is a long solenoid. It's not infinitely long, but as you can see in the results here, and also you can try to derive it yourself, but for an infinite solenoid, this is the magnetic field lah. This is the magnetic field on the axis, and instead, if we have a long one, right, then it's approximately this value lah, because if we take it at the center. At the outside, the issue is that there are edge effects, so you can't really apply this formula exactly the same, because all your flux lines are going to come out lah. Your field lines are going to come out. But at the center, and if it's really long, right, then I think it is safe to say that your magnetic field at this center here is mu naught and I. And I hope everyone agrees with what I'm saying lah. The method we can use to calculate the magnetic field is we can actually attach another solenoid at the end. I don't know if OneNote gives me the space, but let's say we attach another identical solenoid at the end, looking something like this. Okay, so this identical solenoid also has length L. Okay, so it's the exact same long solenoid, right? And we also know that the magnetic field B0 here is also mu naught I, but anyway, it doesn't really matter too much. Okay, so it also has its own magnetic field, something like this. When we combine the two together, it's gonna look something like these. Your magnetic field lines are gonna become straight again in the middle, right? And now you have a twice as long solenoid, length 2L, right? And by the same reasoning just now, right, this magnetic field is also going to be mu naught M I. I think that's pretty safe to say that's correct, because it's also a very long solenoid. Is this like superposition? Yes, it's superposition. Yes. Basically, the point I'm getting to is that in your original setup, here your B1 is also the same as here, right? So when we superimpose this other solenoid here, right, this B1 is also present here, actually. So your net magnetic field here can also be expressed as 2B1. And this is your B0 lah. So that just gives us that your B1 is half B0 lah. And that's exactly what we wanted to show. We wanted to show that the magnetic field at the end is half that at the center. And we're done with the problem actually. That's it. We didn't have to do any complicated integration whatsoever, but we got the answer anyway. And it's just using a matter of superposition. And this is actually an important example to illustrate how important superposition can be sometimes. It can really help. Yeah, that's problem 2.3. I appreciate the effort for integration. And to be fair, it also works. It's just, if there's a faster way in the competition, you probably should take it. And this is a really fast method. It's basically one step. Okay, that's 2.3. If there's still any question request, you can just send it and I'll go through it. Okay, next one is from 2.12. So let me draw out the situation. Something like this. Something like this. So we have two hollow infinitely long concentric cylinders. Okay, this one has radius a, this one has radius 4a. All right, so both of them are insulators. Inner one has a charge per unit length of plus lambda. Outer one has a charge per length of minus lambda. And the inner cylinder is also rotating clockwise about its axis. So it's rotating in this direction, something like this. It's at some velocity omega. And this omega is relativistically slow. So basically just don't consider relativity lah. Yeah. And we assume the permeability of the dielectric cylinder in the space between is that of free space, whatever. Yeah, it's just like that. The first question is to determine the electric field in all regions, which this one you should know how to do by your electrostatics chapter already. What we want to do is we take some surface like this, right? This is your Gaussian surface, okay? And we want to consider the flux out of it, right? So we have by Gauss's law, right? What we can say is that this integral of your E dA, okay, sorry, ds, I'll use ds, is your Q enclosed over epsilon naught. So how exactly do you use that? The integral of the E over the area, right? Your electric field should be radially symmetric lah. And yeah, that should be pretty obvious, right? And it doesn't really depend on the motion it doesn't really depend on the rotation, by the way, because the rotation, this only really generates magnetic fields. But the charges themselves, they already emit an electric field whether they're moving or not lah. So we have the electric field outwards is radially outwards, and it is also the same everywhere and points along the direction of ds. So this integral simply evaluates to E multiplied by the area of this cylinder, which is 2 pi. My brain died. 2 pi RL. Yes, this is the length L lah. We take this to be L. I know it's infinitely long, but we're just considering some small segment. And technically, you also need to consider the flux through here, but it should be quite obvious why there's none of this direction here, right? So we don't really need to consider it. There's no flux through each of these surfaces. And even if there was some direction, right, they cancel out on both. Yeah. So E times 2 pi RL, that's this integral. Q enclosed over epsilon naught, that depends on your setup. So that depends on your radius. So this is actually by cases, right? So this is lambda L over epsilon naught in the case that this radius is in between A and 4A. This is this expression, right? And it's 0 otherwise, which I think it should be pretty easy to see. If it's inside, you're enclosing nothing. But if it's outside everything, you're enclosing everything, which includes both the plus and minus, so they both cancel out lah. So this is your case wise lah. And with that, you can then calculate the electric field easily lah. Your electric field will then be, again, we can split it into cases. This 2 pi r epsilon naught for between these two radii and 0 otherwise lah. Yeah, so that's your electric field. This should be your electrostatics. It's not that difficult. Your second question is to calculate the magnetic field for all regions. And this is, I think in a similar spirit, right? We then use Ampere's law, okay? So this time, right, let me see if I can redraw the diagram. Give me a moment. So it looks something like this. Actually, I don't even need the outer cylinder, as you can see later, but because it's not rotating, so it doesn't really generate any current. So we have this cylinder here, right? What we're gonna do, I'll use the magic pen actually. What we're gonna do is we consider some. This is gonna be our loop, okay? So it goes in this direction, something like that. And basically, this is the loop which you're going to be considering the Ampere's law on lah. And how exactly we do that is that this thing is actually very, very big lah. So this is basically infinite lah, I guess. And what we're going to do is we consider Ampere's law on this. So to do that, we can integrate the, I'll change the normal pen now. We can integrate your B dot dl along this, and we can equate it to mu naught I lah. So what's your B? Your B, right, should be obviously tangential lah. That is by the exact same reasoning that we've already done. Oh sorry, not sorry. Oh my god, sorry, I'm crazy. Sorry. It's rotating like this, right? So actually, a magnetic field should be pointing along the axis of the cylinder. That's my bad. Yes, it should be pointing along the axis of the cylinder, right? So that means if we've taken this direction to be like this, yeah, if you've taken this direction like that, right, your B field is going to point parallel to it, right? So along this line segment, right, this integral is going to evaluate to B times the entire length lah, BL lah, right? Then we want to consider the integral along the rest here. But that's even easier because it's all zero. The reason is because, again, since it points along like here, right, it's going to be perpendicular to both of these. So your dot product is going to evaluate to zero. And here, right, since we did this to be basically infinitely far, the magnetic field here is basically zero. So the rest don't actually contribute anything. So these contribute nothing. That means our integral is just BL. Okay. Then all it's left to do is to consider mu naught I enclosed, which again can be done quite simply by just considering the segment lah. So in this case, right, inside the cylinder, right, inside the cylinder, this enclosed amount is going to be lambda L omega over 2 pi. Lambda L over 2 pi. And this is zero otherwise. So this is within the cylinder. This is outside the cylinder. And this should be pretty easy to see because this is charge. This quantity here is charge, and this quantity over here is the period. So you basically just get the current that's enclosed inside. For angular speed, I thought I had to do integration to find the current. No, you don't, because here, right, the current that is enclosed within this loop, right? Let me see if I can draw a better diagram, right? It looks something like this, and it's cutting through this surface stuff. Pretend it's cutting through this surface. So this cylinder is like rotating lah at some speed omega. The charge that is passing through this like surface is going to be lambda L, and you're gonna have the period as omega over 2 pi. Sorry, 2 pi over omega, and you're dividing by it lah. So this just gives the current that's enclosed inside lah. You kind of get what I mean, right? Like if you look at these quantities separately, this is the charge, this is the period, inverse period. Yeah. So this is the enclosed lah. But that only applies if this line here is inside lah. Basically meaning your radius is you're considering is basically just means that the radius you're considering is within that lah. Yeah. So it only applies if R is less than A. Take into account the different current at different points. No, the current is the same everywhere. I mean, that's just by symmetry lah. The entire cylinder is rotating. Yeah. Yeah, pretty much. Yeah. So anyway, that's this expression. So we just divide by L. Oh my god. There it is. Yep. So we just divide this by L, get rid of this, and we get our B is this. If we get rid of the L. Mu naught lambda omega over 2 pi. Yeah. That's only if it's inside and 0 if it's outside. Yeah. Now, our final question is to calculate the pointing vector. This pointing vector, you don't really need to know what it is, but it's basically sort of a vector that points along. It sort of means the propagation of energy, sort of. Yeah. But here it doesn't really matter. They just ask you to determine the pointing vector in all regions. And it turns out this is really easy. Why? Because all you need to do is you consider the ranges involved, right? Within R is less than A, right? This B is non-zero, but your E is 0. But outside of this range, even though your E is possibly non-zero, this B is 0. So actually, right, this pointing vector is 0 in all regions, actually. So the question is actually kind of simple. Yeah. And that's it. So this entire question was just a basic application of Gauss's law and Ampere's law. And the pointing vector just turns out to be 0. And that kind of just means that no energy is being propagated throughout the system. And that's only really because it's non-relativistic. But you don't really need the nitty-gritty details. If this came out in SPhO and they asked you to do it, just do it. Yeah. Okay, that's it for this question. Do you still have any questions about this? If not, I'm going to move on to 213. Okay, I think I'll just move on to 213. So, 213. An electron and a positron, a particle of the same mass as an electron but opposite charge, are separated by distance this in a region of uniform magnetic field that is perpendicular to the line joining both charges. Given that the two charges are released simultaneously from rest, find the minimum distance that is achieved throughout the motion. This is not very, very nice, but this involves the idea that has actually been mentioned here. Yes, this actually requires the exact same idea. I need to pull up the solution though, because I don't remember it from heart. But just give me a moment. I need to pull it up. Also, I'm too tired to derive from the spot, but just bear with me, because I have the solution somewhere. Ah, there it is. Okay, so let me go back to the question and let me just draw it out. Okay. An electron. Okay, and if you don't know, by the way, a positron is just a particle with the same mass as electron, but that's opposite charge. So it's not like a proton, which is heavier. It's just the same mass, but it has different charge. So if an electron and a positron, right, they're separated by some distance and region of a uniform magnetic field that's perpendicular to the line joining the charges. So your B might look something like this. Yes. And the two charges are released simultaneously from rest, and you want to find the minimum distance that's achieved throughout. So it looks a bit difficult because again you might want to solve the equation of motion. That'd be really tedious. But the important thing to note is that, okay, first off, how would it move? Because these two want to attract each other, right? But when they attract each other, they're gonna start accelerating and they're gonna have a velocity. When they have a velocity in this direction, right, your B field is gonna deflect it in some other direction, and these are gonna cause these charges to rotate. Yeah, which is very annoying. But let's just do it slowly. Let me change the direction of the magnetic fields actually. Let me make it point in this direction. Something like this. Yeah, so your magnetic field now points into the page, okay? So let's suppose that the positron and electron move something like this because of their motion. And why like this? Because they are deflected. So, actually is that the right direction? Sorry, let me make this positive. Let me make this negative. Yes, so this is the positron, this is the electron, and they move like this, okay? What we're going to do is, at some point in their trajectory, we're going to consider the electric force as well as the magnetic force. And obviously this magnetic force is perpendicular to the trajectory, because that's magnetic force. It's always perpendicular to the velocity. And at some point they're going to reach their minimum velocity, something like this. Yes. So what do you want to do? We want to consider the motion of the electron, right? The first thing to do is to actually calculate their potential. We actually want to use the conservation of energy lah. This is again based off the conservation law that we mentioned previously, right? So the first thing we do is use conservation energy. What does it tell us? The initial electric potential energy between these two is going to be the final electric potential energy plus their kinetic energy. And here they gain kinetic energy because although the magnetic field doesn't do work, clearly the electric force is doing some work lah. So there's gonna be that. But that's why there's no MPE here lah, magnetic potential energy, because in the first place it doesn't do any work. Yeah. So if we equate those, right, we get these two equations, minus q squared over 4 pi epsilon naught r naught. This is your initial electric potential energy. That's going to be equal to your final potential energy, which is minus q squared over 4 pi epsilon naught r. This is at some arbitrary distance r lah. Yeah. Then you add the two kinetic energies of them lah, which is just mv squared, right? And by Pythagoras theorem, we can rewrite this as Vx squared plus Vy squared. So this is our statement of the conservation of energy. Next, what do you want to do? When the distance between the positron and the electron is minimum, obviously the x velocity is going to be 0, because here we're taking the x to be in this direction, and let me draw that down. Here we take the x to be in this direction, and here we take the y to be in this direction. So when they're at the minimum, obviously Vx is going to be 0. So this thing is going to die lah later, right? So all we need to do is we need to find the vertical, this Vy lah. And all we need to do is we do it in a sort of similar way to just now, where we just consider the force along the y-axis. And clearly, that y-axis force is only contributed by the magnetic force. The reason the electric force doesn't contribute is because it's always going to be pointing along the x direction, because you can see that the trajectory is going to be symmetric lah, obviously. Like if you think about it, I'll let you think about it, but it should be always symmetric. So the only thing that's contributing to the change in the velocity of the y velocity is this magnetic force, right? So that's just Newton's second law, right? Okay, not Newton's second law, we just consider the force. So the force in the y direction, right, is going to be your magnetic force multiplied by the cosine of like this angle over here, because the cosine gives this, so this is going to be your Fy, right? And this angle is also the same as the angle between your velocity and the electric force, because if you think about it, you just take this electric force, you rotate it 90 degrees, you take the velocity, you rotate it 90 degrees, the angle is preserved, but then you take one and you map it to the other. So I hope it kind of makes sense why these angles are the same lah. But yeah, anyway, we get that this this y component of the force F is going to be your magnetic force multiplied by cosine of theta, right? And this is just going to be B, so this is just going to be QV cos theta B, right? And what's V cos theta? V cos theta, right? Again, we have this relation here, right? V cos theta, this is just Vx, right? So this is actually just QVXB. Yeah, and actually we're very close now, because this Fy is just MAY lah by Newton's second law, right? So we have MAY is QVXB. And we're already very close because as we demonstrated in the previous example just now, right? We're in the perfect position to eliminate time now. Because now all we need to do is rewrite this as a differential equation, right? M dvy over dt is q dx dt b. Yes, this is what your differential equation looks like now. Consider magnetic force by the other particle. There's only one magnetic force here, right? Oh no, we know. Oh no, here I think we're ignoring it. I get what you mean. There could be a magnetic force that is produced by this, right? Because here, if it's moving in this direction, it's gonna, by right hand rule, it's gonna generate one that's like upwards, like here or something like that. So it's gonna be upwards here, but here we're neglecting it now. We're assuming that doesn't exist. Yeah, because we're assuming that the magnetic field here would be much larger than the ones that are produced by the electron moving. Yeah, so it's fine. We're free to ignore it. If not, it will become too complicated. But yeah, anyway, aside. So MAY is QVXB, and we can do this. And once again, we can do the same trick of eliminating time, right? So we get MdVy is QBdx, and we can then just integrate this thing, right? That's quite easy. All we do is we get MVy is QBx plus some constant, right? But this constant is quite easy to find. Then if you solve for it, you get that your Vy is QB over M times R, sorry, times R naught minus R over 2. You can show this yourself, you just need the initial conditions. Yeah. So this is your vertical velocity in terms of the distance between them lah. So all that's left to do is we just need to substitute the expression for Vy, right? So we take this and we substitute it there. What does that give us? Let's write the whole equation. We get, sorry, I'm struggling to use this. Q squared over 4 pi epsilon naught. We bring this over to the other side. We get 1 over R minus 1 over R naught is mvy squared. So we get Q squared B squared over M R naught, oh my god, I don't have space, minus R over 2 squared. Yeah, this is your equation now. And what's left to do? Just solve, right? Because this is actually a quadratic equation. So I'll let you figure it out. But you can get a quadratic equation and you can get the solution to be, let me write it out. This goofy expression here, B squared R naught over 2. Yeah. And here you take the valid solution, but because the other one is plus, but obviously doesn't really make sense. But yeah, so this is your minimum R lah. You're done actually. That's it. And you can substitute the values that they give by yourself lah, but that's not really the point. The point is that here it's a little more complicated than the example that we presented. Where is it? It's a little more complicated than the example that we presented here, because here the main thing is that we only have a magnetic field, right? This magnetic field, and there's no electric field, so the speed is constant everywhere lah. But in this example, But in this example, instead, there's still an electric force that are acting between both of these particles. But it's still fine because there's still some aspect of symmetry to it where their trajectories are going to be symmetric, right? That means that your electric force is only going to point in this direction. And when we consider the vertical velocity, we only have Fb. And with all of that bashing, we eventually get something that we can integrate again. And it's even easier this time because it's just v. And yeah, that's the whole problem lah. Are you still confused about it? Because I know my explanation was not very well said, but I think you should be able to understand it, right? Basically, we apply the conservation of energy here, and then again, we consider the magnetic force here. The magnetic force exerts some acceleration on it, and then we find that it's only dependent on the x velocity lah. Then from there, we eliminate the time dependence. We can integrate to get Vy in terms of this distance x between them. We can solve to get Vy in terms of that. And then we can substitute back into the conservation of energy with the condition that Vx is 0 at the minimum distance. We solve and we get the distance. Okay. Okay, cool. If so, I think that should end the session. It's 10 p.m. If there's any other questions, you guys can still message any one of us. But please try to do the rest of the problems. It will help you a lot, I think. Yeah. Okay, some of the problems, to be fair, are pretty easy. So if you're already familiar with the concepts, I suggest you can do them for a recap, but it's not necessary. Some of the later ones are more interesting, though they're more difficult. So if you're willing, if you're up for a challenge, you can do it, I guess. Some of the concepts are also like kind of repeated, but it is good exercise though. And there are also a few more challenging ones here. There's SPhO, there's Kevin Cho here, I guess. This one is kind of difficult, honestly, so if you don't do it, don't be disheartened, but yeah. And there are also a few advanced problems that you can try if you're at that caliber. If you're not, it's okay. But yeah, I suggest you can do some more problems if you don't understand. And please feel free to ask any of us if you have any clarifications about this topic lah. Yeah. So I understand it's my first time teaching, so it can be a little bit difficult to understand, but I hope you understand. Yeah. If there's nothing else, I think we can call off this session here. Thank you for coming, everyone.